Okay, so we spend a lot of time on whole numbers, but I feel it's the best way to get our basis for everything else. Let's kind of tie it all together with our other forms of numbers here for today. First type of number I want to look at is this. -4. Negative numbers. Combined with our whole numbers, they make up what we call the integers. So when you hear that term integers, all that means is it's possible for some of the numbers to be negative. To understand how to work with integers, we're going to go back and we're going to take a look at just working with the counts, the amounts of a number for a while. And to deal with that, we're going to use the number line. To represent a number on the number line, we can use just a dot if we wanted to. We could put a dot at -4, but that's not really useful mathematically. The way we represent numbers on the number line to make them useful is we use something called a vector. Now, a vector is just a really fancy word for a very simple concept. It's an arrow that starts at 0 and goes to the number. So there's -4, just like that. And we use these vectors to define our operations. For example, 5 plus 3 is telling us take a vector for 5, take a vector for 3, and we're going to mechanically combine those, put them together, and we get 8. It goes up to 8. So addition is the process of mechanically combining these vectors. Now multiplication, let's say I have 4 times 3. What that is we talked about repeated addition. What that's telling us to do is to take the vector for this 4, which is just like this, and make 3 of them, and put 3 of them together, like that. That's multiplication. Now again, subtraction and division are defined through addition and multiplication, so that those don't really appear on the number line, but we'll look at that in a minute. So with these definitions of addition and multiplication out there, let's look at doing some operations. Now, I'm not going to worry about the positive numbers because we've worked with positive numbers enough that we can handle that. But let's take something like 8 plus a -3. Now, your book usually just puts parentheses around that negative number just to show you that's not subtracting 3, it's the negative is with the 3. So you have 8, like that, -3, something like that. And when we add them, we put the vectors together. And unlike the 5 plus 3, where the vectors built on each other and made it longer, here, because one of those vectors is negative, they actually work against each other, and they cancel out, make something shorter, give us 5. Make sense? Now, I'm not expecting you to draw out a number line. In fact, it'd be very tedious to draw out a number line every time you do addition with integers. But I keep that picture in my head as I'm doing them. For example, I might have a -12 plus 7. When I'm doing that, I'm doing this. I'm going to make a 0 point. -12 looks like that. Goes in the negative direction. Now, 7 is positive, so it goes the opposite direction. Is it longer or shorter than the 12? It's shorter, so it goes in the opposite direction, but it's shorter, so it doesn't get all the way back to the end. This picture tells me 2 things. 1, I ended up on the negative side of 0, so my answer is negative. 2, the vectors go in opposite directions. So the size of my answer is just the difference between 12 and 7, which is 5. And there's only 2 possibilities. The vectors can either both go the same direction, where we combine or add the values, or they can go in opposite directions, where we subtract or cancel the values. For example, we could have -9 plus -8. Well, here, if it's 0, -9 goes this way. Well, -8 goes the same direction. So that's telling us that pretty obviously our answer is negative, but since the vectors or the arrows point in the same direction, we're adding the values. 9 and 8 make 17. It's a -17. We could have -8 or -6 plus 13. Here's 0. There's -6. 13 is positive, so it goes the opposite direction, and it is longer. So we go past 0. So that's telling us that we get over into the positive range. And the arrows go opposite direction, so it is the difference between 6 and 13, which is 7. So it's a positive 7. And with larger numbers, it works just the same. We might have 247 plus a -116. Well, here's 0. There's positive 247. -116 goes the opposite direction, and it's shorter. So that tells us the answer here is going to be positive. The arrows go in opposite direction, so it's the difference between 247 and 116. So I'm just going to subtract them. So it's a positive 231. Oops, 131, I should say. So positive 131 is our answer. What do you think? Better than a sharp stick in the eye? So far, at least? Okay. Subtraction is where it starts to get ugly. Remember we said subtraction isn't its own operation. And most of the confusion with subtraction comes from the fact that most people have been taught that subtraction is its own operation. So we have to get that out of our head and start thinking of subtraction as being part of addition. For example, let's do 8 minus 3 and see where that takes us. On the number line, if we had to illustrate 8 minus 3, we'd probably do it like this. There's 8, subtract 3, we're at 5. Because we all know 8 minus 3 is 5. But if we look at that picture here, that picture looks exactly like the picture for 8 plus a -3 that we just did up on the top of the previous page. It's because it's the same problem. This symbol here that we know as the subtraction symbol, actually we combine it with the number that comes after it, is a shortcut. It's an abbreviation. -3 is telling us add the opposite of 3. Or add the opposite of this number that follows. So 8 minus 3 really means 8 plus the opposite of 3 is -3. So if I have 9 minus 7, that really means 9 plus a -7. Now realistically, 9 minus 7, I know that's 2, so I don't need to change it. But where I do need to change it, what does help is if I have a -12 minus 5. A lot of people get confused there and would say it's -7. It's not. This is -12 minus 5 means plus the opposite of 5, so plus -5. Well, now -12 and -5 make -17. The arrows go the same direction, so they build on each other. Once it's been converted to addition, we can go back to that vectors that we used for addition, and it's fairly simple from there. The one that's always a crowd pleaser is one like this. 7 minus a -5. Remember, this symbol means add the opposite. So we're going to add, what's the opposite of -5? +5. Subtracting a negative becomes adding a positive. 7 minus a -5 is the same as 7 plus 5, which is just 12. Or if we have -13 minus -4, that's going to become -13. And of course, a lot of people look at that and say -17, but it's not. It's plus a +4. So here's 0, -13 plus 4 is a -9. What do you think? That one will take a while to get used to. In my opinion, the two hardest skills in math. The first hardest skill is taking a word problem or a set of words and turning it into a formula. The second most difficult skill in math right there. Subtracting with integers. It's just the negatives tend to get you all messed up. And we throw subtraction in there as well. It really confuses things. Always, always change it to plus the opposite. Okay, excuse me. Multiplication. We've already looked at multiplication. 5 times 3 is being 5 plus 5 plus 5. Or having the 3 vectors for 5 added together to get 15. So negative 5 times 3, well, that's pretty obvious. Negative 5 plus negative 5 plus negative 5. Or having the 3 negative vectors for 5 combined together, which is just negative 15. One that makes a little less sense is this one. This is okay, taking negative 5 and putting 3 of them together. That's easy to do. But how do I take 5 and put negative 3 of them together? Well, I really can't. So we just switch them around. We take negative 3 times 5. Instead of taking 5 and adding it negative 3 times, we're going to take negative 3 and combine it 5 times. So you'd have the negative 3, negative 3, negative 3, negative 3, negative 3, which is negative 15 again. Well, again, the one that can be confusing. Negative 5 times negative 3. Now, all of us have been taught that that answer has to be positive 15. Because it's been pounded into us. A negative times a negative is a positive. But if you look at it through the definition of multiplication, can I take negative 5 and add it negative 3 times? Well, that doesn't make sense. Can I take negative 3 and add it negative 5 times? That makes no sense either. According to the definition of multiplication, this cannot be done. We run into that actually quite often in math. And what we do is we look for a pattern. We look at other problems that are related to it that can be done. And we see if we can use that to just define what this answer has to be. For example, we said negative 5 times 3 is negative 15. What's negative 5 times 2 have to be? Negative 10. Negative 5 times 1? Negative 5. So if we look at this, if you look for a pattern, when we start with negative 5, if we take what we're multiplying by and we reduce it by 1, when we go from 3 down to 2, we reduce by 1. The answer goes up by 5, from negative 15 up to negative 10. From negative 10 up to negative 5. So let's keep going. Negative 5 times 0 has to be 0. And again, the pattern continues. We went down by 1 here. This goes up by 5. So it looks like that pattern holds. So now we're just going to continue the pattern. Negative 5 times negative 1. Well, this went down by 1. This goes up by 5. So it has to be positive 5. Negative 5 times negative 2 has to go up by 5. That's 10. Negative 5 times negative 3, well, it's got to be a positive 15. So we define negative 5 times negative 3 to be a positive 15 because it fits the patterns. Like I said, that happens a lot in math where our basic definition doesn't work for a problem. So we just go back and we look for the pattern and we define the answer to be whatever fits that pattern. So let's say we have like negative 7 times 6. What's that going to be? First of all, positive or negative? Well, negative times a positive will be negative. Then 7 times 6, 42. So negative 42. 8 times a negative 4. Positive or negative? Negative. Whenever there's one of each when we multiply, the answer will be negative. A positive times a negative or negative times a positive. And then we just do the numbers. 8 times 4 is 32. How about negative 9 times a negative 5? Positive or negative? Positive. 9 times 5 is 45. Division, we're not going to waste a lot of time on it. Follows the exact same rules. 36 divided by a negative 4. Well, positive divided by a negative will be a negative. 36 divided by 4? 9. Or 24, negative 24 divided by 6. A negative divided by a positive will be negative. 24 divided by 6 is 4. Negative 40, divided by negative 10. Well, a negative divided by a negative will be positive. 40 divided by 4 is 10, so positive 10. Next step. What's that mean? 8 cubed, right to the third power. And we would calculate it by doing 8 times 8 times 8. It's repeated multiplication. It means 3/8 multiplied together. Now that one you could probably multiply out with your calculator to get 512. But if I give you something like 2 to the 12th power, you don't want to be sitting there doing 2 times 2 times 2, trying to keep track of, did you do 12 or 11 or 13? On your calculator, there's a button. Most of your calculators have a button that looks like that. It's called the caret key. On the TI-30 calculator, it's off on the left side about halfway down. If you have a one-line display, it's over on the right side, about the second or third key from the top. It's an X to the Y key or Y to the X key. So you punch that in, 2 to the power of 12, you should get 4,096. If you want to test it out to make sure you know how to use the key right, go ahead. If you don't have a calculator yet today, that's fine. You can practice at home. You get to work? Cool. That right there is the main reason why I recommend a scientific calculator. Because if you just have the little 5-function calculator, they don't do powers, and that can be a real pain. Getting it to work back there? Yours work? Yours doesn't have it? Here, let me take a peek. So we can do those powers. And we're not going to spend a lot of time on it right now because it's not a huge deal in the medical field. What is something that's going to be important when we're doing our dosage calculation is this. What's that symbol mean? Square root. And the square root is actually kind of like addition and subtraction are kind of reverses of each other, and multiplication and division are reverses of each other. A root is actually the reverse of a power. 5 squared equals 25. Therefore, the square root of 25 is 5. Square root and power of 2 are squared, reverse each other. There are other roots out there for other powers. For example, 4 to the power of 3 is 64. Well, there's something called a third root. The third root of 64 better be 4. Most of your calculators have that square root key. Now, depending on which calculator you have, if you're going to do a square root of 121, some of you would have to hit the square root key first. In fact, many of you would have to use a second or a shift key because the square root key is actually above one of the other keys. So you use the second or shift key and press square root, type in 121 and hit equals. Or some of you would have to type in the 121 first and then hit the square root key, and it should spit out 11. As more of you get your calculators, if you work on problems like that, let me know and I'll help you figure out how your particular calculator works. Okay, so now we've exhausted our whole numbers and our integers. Let's get as much of our fractions done as we can today, and then we'll pick it up next week. We've talked a little bit about fractions already, and the idea that just like any other number, when we add fractions, we must have the same name. So with fractions, that means a common denominator. Here we have fifths and fifths. And when we go to add, we're just going to combine the counts, combine the numerators, 1 and 2 make 3, and keep the same name. You guys got to head off to the other class? Okay. So when we run into fractions that don't have the same denominator, don't have the same name, the first thing we have to do is figure out how to give them the same name. So let's say I have 1/4 plus 3/5. To figure out what name they need to be given, we have a couple processes we can do. One is we could just multiply the two of them together. 4 times 5 is 20. That's always going to give us a common denominator. Now, most of us were told you have to find the least common denominator, the smallest one. That's not true. You can use any common denominator. It's just when you get done, you're going to have to reduce the answer. It's just easier. It's a lot less work if you find the least one. To find the least one, there are a couple of different things you can do. Probably the simplest way is to make lists. They're counting up by 4s, 4, 8, 12, 16, 20, 24, and so on. Then with the 5s, you count up 5, 10, 15, 20, and we have a match. So 20 does turn out to be the least common denominator. So we're going to change these into 20ths. To change the 4 into 20, we didn't go over renaming fractions. We're assuming you guys can do that. The only way you can rename a fraction is to multiply or divide the numerator and denominator by the same number. So to change a 4 into a 20, I have to multiply it by 5. So I have to do the same thing to the numerator. 1 times 5 is 5. 1/4 and 5/20 are the same thing. They just look different. The same down here. I'd turn the 5 into a 20. To do that, I have to multiply it by 4. So 1 times 4 makes 4. Oops, that's not supposed to be 1. That's supposed to be 3. Let me fix that. 3/5. So 3 times 4 is 12. So it's 12/20. I didn't write down my problem right. Now that we have the same name, just like always, we combine the counts. 5 plus 12 is 17, and we keep the same name of 20. Now, we're not going to waste a lot of time with simple fractions in addition. We're going to jump up to mixed numbers. And I'm just going to start writing them vertically because that's how I work with any addition. So we might have like 8 and 8 1/6 plus 5 and 3/8. So again, we have to find that common denominator. We're dealing with 6 and 8. We could make lists and count up. What are we going to get for that common denominator? 24 ends up being the right one. Good. If anybody really struggles with that common denominator, there are a couple of other ways you can find it. I don't want to take class time for it, but I'll show you outside of class some other ways to find the common denominator. So we have to turn the 6 into 24. What do we multiply it by? 4. So 1 times 4 is 4. How do we turn the 8 into 24? Times 3. So 1 times 3 is 9. Now, you can see I have that fraction just sitting at the end there, lined up, just like it's the last digit of the number, because that's all it is. It is the last digit of the number. So we're going to combine 4 24ths and 9 24ths. Combining the counts, 4 and 9 is 13, and you keep the same name of 24. And we move on to the left. 8 and 9 is 13, so it's a 3, carry the 1. So 13 and 13 24ths. So we might have 6 and 5/6 plus 18 and 3/4. Common denominator will be 12. What's this going to become? That'll be a 10. And this one? 9. So now we go to add. We start on the right, working our way back to the left. 10 and 9 make 19 12. So what's wrong with that? It's more than 1. Yeah, we can reduce that into 1 and 7 12ths. So just like with whole numbers, we'll leave part of it. We're going to leave the fraction, the 7/12, and we're going to carry the 1. 1 and 6 makes 7, plus 8 is 15, so 5, carry the 1. 1 and 1 makes 2. So 25 and 7/12. Any questions? When we go to subtract, I'm going to jump right into mixed numbers with subtraction. It works the same way. We need a common denominator. For thirds and fifths, it's going to be 15. Good. One way I always do it is you can just multiply them. 3 times 5 is 15, and then see if there's anything smaller. You know it's not going to be bigger than 15. See if there's anything smaller than 15 that they can both go into. This is going to become 10. Good, because 3 times 5, so 2 times 5. This will be 6. We go to subtract. 10 minus 6 is 4/15. 8 minus 5 is 3. That's not so bad. So here, common denominator will be 12. This will be 3 and 10. We go to subtract now, however. 3/12 minus 10/12 gives us a problem. Just like with whole numbers, we're going to borrow. From the 9, this is going to be 8. What's this going to become? What we borrowed was one whole object, which is 12 pieces. So we have to be careful. What we borrowed here, every one object contains whatever the denominator is for pieces. So there's 12 that we add on to the 3 to get 15/12. If you think of it, we borrowed 1. 1 and 3/12 is 15/12. So 15 minus 10 is 5/12. 8 minus 2 is 6. Let's do another subtraction with borrowing, just because that one's a little more difficult. Bless you. So let's do 28 and 2/5 minus 19 and 7/8. Common denominator will be, no getting around it, it's going to be 40. So this will be 16 and 35. We go to subtract. Obviously, we can't do 16 minus 35, so we need to borrow. That's going to be a 7. What's this going to become? Plus 40. Good, because the denominator is 40. We add 40 to the numerator. We get 56/40. Now it's 56 minus 35 is 21/40. 7 minus 9 can't be done. We're going to borrow. That's 1 and 17. 17 minus 9 is 8. Let's do some multiplication. Yep. Well, I had a 7 minus 9, which you can't do, so I had to borrow from the 2 to make it a 1 and a 17. So 17 minus 9 is 8. 1 minus 1 is nothing, so I didn't need to do anything there. When we multiply, we saw earlier that we just multiply straight across. And that's exactly it. We combine the counts. 2 times 3 is 6, and we also combine the names. 4 times 5 is 20. Now in this case, we see that we can reduce that. Both the 6 and the 20 can be divided by 2 to give me 3 and 10. Some of you might have been looking at that original problem thinking, why didn't you cross-cancel? Others right now might be thinking, what's cross-canceling? Well, when we multiply this, this is going to be 3 times 2 over 4 times 5. And one of the things we can do with fractions, as we said, we can multiply the top and bottom by the same thing, or we can divide the top and bottom by the same thing to reduce it or simplify it. we see here that we've got a 4 and a 2 that can both be divided by 2. So rather than reducing later, we can reduce before we multiply. The 4 and the 2 can both be divided by 2 to give me 1 and 2. Now when we multiply, 3 times 1 is 3, 2 times 5 is 10. So we get the reduced answer. Now in a problem like this, it is about the same amount of work either way, to either cross cancel and then multiply, or just multiply it out and reduce. But we can run into problems like this. 24 25ths times 35 36. Where if we were to multiply this out, this is going to be, 840 over 900. And then you'd have to reduce that. Or we could look at this and realize 24 and 36 can both be divided by 12. So this is 2 and 3. 25 and 35 can both be divided by 5. Give me 25. Give me 5 and 7. So now 2 times 7 is 14. 5 times 3 is 15. If you were to reduce this, it would reduce to 14 over 15. It just takes a while to get there. So again, I'm not going to spend a lot of time multiplying simple fractions. We're going to go to mixed numbers. Let's multiply 7 1/3 times 4 2/5. Multiplying mixed numbers is actually a really difficult process. In fact, if I were to go over here to the UW and find 10 math majors, I bet none of them could correctly multiply mixed numbers. So what do? We avoid it. What we do is we try to turn them into improper fractions. 7 1/3, what we can do is the 3 is telling us that each whole piece has, or each whole object has 3 pieces in it. So 7 times 3 is 21, plus the 1 that's already there, that's 22/3. Does that look familiar? Yeah. Okay. If everybody's really struggling with that, let me know and I'll go over it more with you. So we've changed that 7 1/3 into an improper fraction. The 4 2/5, same thing. 4 times 5 is 20, so that means there's 20 of those pieces in the 4. Plus 2 is 22/5. Now we can multiply. 22 times 22 is 44. 3 times 5 is 15. But now we have to reduce that back down into a mixed number where we have a whole number and a fraction. The easiest way to do that is to just do long division with a remainder. Now, many of you have fraction calculators. If you figure out how the fractions work, it'll do that for you as well. If you have one and you don't know how it works, let me know and I'll sit down and show you how to do it. But anyway, 15 goes into 48 3 times. That's 45. There's 3 left over. Bring down the 4. 15 goes into 34 twice. 2 times 15 is 30. There's 4 left over. So that's 32 4/15. Just for the fun of it, let's show you how you would actually multiply those as mixed numbers. So 7 1/3 times 4 2/5, right? Yeah. But when we multiply, remember we said every digit in one number has to multiply every digit in the other number. So we have the 2/5 times 1/3, which is just going to be 2/15. But we also have to do the 2/5 times 7. How do we multiply a fraction by a whole number? We make the 7 into a fraction by doing 7 over 1. So 2 times 7 is 14, 5 times 1 is 5, that is 2 4/5. Now we have to do the 4 times 1/3. So 4 over 1 times 1 over 3 is 4/3, or 1 1/3. And 4 times 7, which is just 28. Now we need common denominators. It looks like it's going to be 15, so it's going to stay 15ths. This will be 12/15ths, and this will be 5/15ths. Adding up, 2 and 12 is 14, 19/15ths. which is 1 4/15. Keep the 4/15. Carry the 1. 1 2 is 3, 4, 12, carry the 1, 32 4/15. We get the same answer. I don't know about you. I'm going to stick to using the improper fraction. Let's do one more example of the improper fractions, and then we'll come back to division. Excuse me. Let's do 2 3/8 times 5 1/2. Tell me what to do. 2 times 8 is 16, plus 3 is 19/8. Okay, then what? Ten, 11 halves. You got it. Now, we could cross cancel here, but there's nothing to cross cancel. So we're going to 19 times 11, which is going to be 209. 8 times 2 is 16, and then we have to reduce that back down. 16 goes into 20 once. There's 4, bring down the 9. 16 goes into 49 twice, that'd be 32. Oops. How about 16 goes into 49 3 times? Some days the little hamster doesn't get on the wheel in the morning. There's 1 left over, so it's 13 and 1/16. Now division, just like with whole numbers, division is the one operation that's just been butchered through the years. We said that division follows the same rules as multiplication. And when we multiplied, we just multiplied straight across with our fractions. So does that mean when we're dividing fractions, I can just divide 12 divided by 4 is 3, 25 divided by 5 is 5? Does that work? Well, is that the right answer? It is. Does that work every time? Yeah, it does. So why don't we do it that way? Well, because we run into problems like this. 3/4 divided by 2/3. And 3 divided by 2 is like 1.5. And 4 divided by 3 is 1.333. That doesn't work out so well, does it? What have we been taught to do to divide fractions? We take the reciprocal, 2/3 becomes 3 halves, and then we multiply. Some of you may have learned that it's called the zigzag method, or cross multiply. 3 times 3 is 9, 4 times 2 is 8. That's just a gimmick, but it does the same thing. You're taught, instead of dividing by 2/3, you multiply by the reciprocal. So you multiply by 3 halves, or 3 over 2. And now you multiply straight across. 3 times 3 is 9. 4 times 2 is 8. So 1 1/8. Believe it or not, that came from this. And let me show you how. Once upon a time, if we were going to do 3/4 divided by 2/3, what we would have done is this. We would have looked at this and said, we're dividing by 2/3. 2 times 3 is 6. So we're going to rename this by multiplying the top and bottom both by 6. 3 times 6 is 18. 4 times 6 is 24. 18/24 is still 3/4. It's just been renamed. It's been changed. Now we can divide. 18 divided by 2 is 9. 24 divided by 3 is 8. 9/8, or 1 1/8, which is what we had up here. Now, it doesn't look like there's a connection there, but there really is. At one point, somebody realized that if you did this part here, if you divided that first, 6 divided by 2 is 3, 6 divided by 3 is 2. What you always get is just this fraction flipped over. And what's left is 3/4 times that. So they made a special name for that. They called it the reciprocal. And they define division to be multiplying by the reciprocal. So let's do an example of mixed numbers. 5 1/3 divided by 2 1/8. Just like with multiplication, we're going to turn them into improper fractions. So 5 times 3 is 15, 16/3. Now it's still divided at this point. 2 times 8 is 16, plus 1 is 17/8. Can I cross cancel the 16 and the 8? No, because it's still division. It's really tempting, but it's still division. Now this is 16/3 is not going to change. When we change it to multiplication, we take the reciprocal of the number we're dividing by. So 17/8 becomes 8/17. Now we could cross multiply or cross cancel, but there's nothing there that does cancel out. So 16 times 8 is 128. 3 times 17 is 51, which will become 2 and 26 over 51. Okay, so off that assignment sheet that's on Blackboard, you can do the problems on page 7 and 8. Do the problems on page 18 to 21. Now, we didn't go over decimals, but most people handle decimals pretty well. So you can do page 29 through 32 as well. You can skip for now page 23 on order of operations. We didn't get to that. That is where we will start next week, is order of operations. So skip page 23.